Chapter 7, Estimates and Sample Sizes. In 7.2, we're going to be looking at estimating a population proportion. So for example, if I wanted to know the proportion of people who like dogs in the US, that is the number of people who like dogs divided by the total number of people in the US, would give me the proportion. I could take a smaller sample, look at the proportion of people in that sample who like dogs, and what we'll be doing in 7.2 is developing methods to determine how good an estimate that sample proportion is to the population proportion. So to start out, a definition. A point estimate is a single value used to approximate a population parameter. So for example, if we wanted to estimate the population mean, then a sample mean, x bar, is the best point estimate of the population mean. Similarly, a sample proportion is the best point estimate of the population proportion. Look at an example. A survey finds that 60% of 1,501 randomly selected adults prefer Toyota Corollas over Honda Accords. If I wanted to know what my sample proportion is here, in general, we would take the number of people who prefer Corollas and divide it by 1,501, or the total number of people in the sample. However, in this case, it already gives me the proportion of my sample, 60%. Or, of course, we're writing this as 0.6. So the 60%, or 0.6, is my population, my sample proportion, p hat. A confidence interval is a range of values used to estimate the true value of a population parameter. And we sometimes refer to this as CI, for confidence interval. A confidence interval is always associated with a confidence level, which is the probability that a confidence interval actually contains the parameter in question. For example, we could say the 95% or 0.95 confidence interval estimate of the population proportion P is 0.667 to 0.723. That is, we are 95% sure that our population proportion is somewhere between 0.677 and 0.723. A confidence level of 95% says 95% of our samples should result in confidence intervals that contain the true value of P. So for example, in this case, I have my sample, or my population mean, and I take samples and get intervals that I am 95% sure, or rather 95% of the time, my samples will contain that actual population mean value. But every once in a while, I'll take a sample and calculate an interval that does not contain the population parameter. A critical value is the number on the borderline separating sample statistics that are likely to occur and those that are unlikely to occur. So in our normal distribution, a critical value would be somewhere here over on the far right. We called it z sub alpha over 2, and that is the z-score that separates these probabilities that are unlikely to occur, or the z-scores that are unlikely to occur from the z-scores that are more likely to occur. Find the critical value corresponding to a 95% confidence level. A 95% confidence level says that 95% under our normal distribution would be underneath or between my critical value and its opposite on the far left. So 95% should be in this region, this blue region here, which leaves 5% to be split up between the far ends, the tails of my normal distribution. So if I take the remaining 5%, or 0.05, and I split it up into the two tails, those represent my extreme values, then I would get an alpha over 2 of 0.025. So what I want to find is the critical value that has 0.025 to the right. Well, if it has 0.025 to the right, that means it has 0.975 to the left. So we need to find the z-score that has 0.975 to the left. Well, let's look at our normal probability table to do that. I need to find 0.975 somewhere in this table. So let me scroll down, and it looks like we've got 0.975, and the z-score associated with that is 1.9, and we're in the 0, 1, 2, 3, 4, 5, 6 column. So 1.96. So we found the z-score that has 0.975 to the left or 0.025 to the right is 1.96. So the critical value corresponding to a 95% confidence level is 1.96. Find the critical value corresponding to a 90% confidence level. We'll do the same thing. Now there's 10% or 0.1 to be split up into the two tails. So we have 0.1 is our alpha, and if we divide that by 2 into the two tails, we'll have 0.05 as our alpha over 2. So z sub alpha over 2 is the z-score with 0.05 to the right or 0.95 to the left. So again, we'll go look at our table and try to find 0.95 and find the z-score associated. So let's scroll up and we'll find where 0.95 is. But notice, we're actually right in between 0.9495 and 0.9505. In other words, 0.95 is not closer to 1 than the other. So we'll take the z-score that's right in the middle. That is, I can see we're in the 1.6, but we're between 1.64 and 1.65. So the number that's in between those, the z-score that would be in between those, is 1.645. So we found the critical value corresponding to a 90% confidence level is 1.645. 99% confidence levels, 95 and 90% confidence levels are the most common. So let's do this last one and then we'll move on. So we'll find the critical value corresponding to a 99% confidence level. If it's 99%, that means there's 1% left to be split among the two tails. So let's divide 0.01 by 2 and we get 0.005. That is the z-score with 0.05 to the right, which is the z-score that has 0.995 to the left. So let's go to the table and look up the z-score that has 0.995. So we need to scroll up and find 0.995. Again, it looks like we're going to be right in between two numbers, 0.9949 and 0.9951. So we'll take the z-score that is in between those two numbers. That is, I can see we're in the 2.5 row. We're in the 0, 1, 2, 3, 4, 5, 6, 7, and we're between 7 and 8. So we take the z-score to be 2.575, would be in the middle of 2.57 and 2.58. So we found the critical value corresponding to a 99% confidence level is 2.575. The margin of error is the maximum likely difference between the observed sample proportion p hat and the true value of the population proportion. So if we're trying to estimate a population proportion and we've taken a sample and calculated the sample proportion, the margin of error is the maximum likely difference between those two. We calculate margin of error with this formula. So we first find our z sub alpha 2, in other words our critical value, and we multiply that times the square root of our sample proportion times q hat, which is always 1 minus p hat, divided by n, or the sample size. Let's look at an example. In a study of 1,228 randomly selected medical malpractice lawsuits, it is found that 856 of them were later dropped or dismissed. What is the best point estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed? Well, in general, if we're trying to estimate the population proportion, our best point estimate is a sample proportion, or p hat. So we simply need to find 856 divided by 1,228, and that gives us p hat equal to 0.697. So 0.697 is our best estimate at the population proportion, and that is what we call the best point estimate. Now let's construct a 99% confidence interval estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed. So first of all, for a 99% confidence interval, we need our alpha to be 1 minus 0.99, which is 0.001, and then distributing that into the two tails of a normal distribution, we have 0.005 in both tails. Or in other words, to the right of our critical value, we'll have 0.005, which means 0.995 would be to the left. So we need to find the critical value that has 0.995 to the left. So looking up on our z-score chart, we get 2.575. So now we can calculate the margin of error using our formula for the error estimate. Plugging in what we know, calculating all this, we get 0.034 as our margin of error. So finally, we'll construct the interval by taking our sample proportion and subtracting the margin of error for our lower estimate, and then also taking our sample proportion and adding the margin of error for our upper estimate. So finally we get an estimate of the proportion of the population, or in other words, the proportion of medical malpractice lawsuits that are dropped or dismissed, is between 0.663 and 0.731. The last part of this question might be, does it appear that the majority of such lawsuits are dropped or dismissed? Well, again, take a look at the confidence interval estimate that we found. We're saying that the population proportion, or the number or the proportion of lawsuits that are dropped, is somewhere between 0.663 and 0.731. So when it asks for the majority, it means at least 50%, or 0.5. Now this proportion, even though we don't know exactly what it is, we're saying we're very confident it's somewhere between these two numbers, which even the lowest number is above 0.5, or above 50%. So it does appear that the majority of such lawsuits are dropped or dismissed. So a word about notation. We wrote our confidence interval estimate to be the population proportion between two numbers. However, we could have written our confidence interval estimate in this way. This is what we call interval notation. That is, parentheses, the first number, comma, the larger number, end parentheses. And what we're saying by looking at this is just that the population proportion is somewhere between the low number and the high number. Similarly, we could have written it like this with the plus minus symbol. So we take our our sample proportion, and we add and subtract 0.034, and we're saying we're confident that our population proportion is somewhere between the low number that we subtract and the upper number that we add. Suppose we're conducting a survey for a political candidate to determine what percentage of support she will have in an upcoming election. In other words, what proportion of voters will support her. The candidate wants a 1% margin of error at a 95% confidence level, so that whatever results we get, she can be reasonably sure that they're accurate. What size sample do we need to meet these parameters? Let's take a look at the margin of error formula that we saw earlier. So in this case, we know what the margin of error is, and we'll be able to calculate the critical value for a 95% confidence level. What we're interested in is the size of the sample that we need, or in other words, we want to figure out what is this n. So I'm going to do some algebra here to solve this formula for n. It's not so important that you follow the algebra, but rather at least understand the end result. So the first thing I would do to start solving for n is square everything. So if we square e, we'll get e squared. If we square our critical value, we get our critical value squared. And if we square the square root, we have no more square root. Now I want to get n on the other side of this equation and out of the denominator of the fraction, so I'm going to multiply both sides of this equation by n. Now, of course, the n's on the right side will cancel out. Now I'm left with n times e squared on the left, and my critical value times p hat times q hat on the right. So what I'll do next is, in order to get n by itself, I want to divide both sides by e squared, which is the same thing as multiplying by 1 over e squared on both sides. So divide by e squared on the right, and of course on the left the e squareds cancel out, so I'm left with n by itself. Let me multiply these two fractions together. Leaves me with n equal to my critical value squared times p hat times q hat divided by e squared. Now I didn't mention this, but we don't actually know what p hat is. In fact, that's what we're trying to find out. So if we don't have any good estimate of what p hat is, we're just going to use 0.5 for p hat, which means q hat will be 1.5, or in other words, also 0.5. So we're going to use this formula. 0.5 times 0.5 is 0.25. We'll use this formula anytime we don't know anything about p hat. So back to this problem. We know now that n is our critical z-value squared times 0.25, since we don't have any information about the sample proportion we're expecting, divided by the margin of error squared. That was 1.96 squared times 0.25 divided by 0.01 squared, which is 0.0001. Throwing all this into the calculator gets us 9,604. So our sample size, in order to have a 1% margin of error at a 95% confidence level, would have to be 9,604 people surveyed. Quick note, if the computed sample size is not a whole number, we always round up to the nearest whole person, or the nearest whole number. We want to obtain a sample to estimate a population proportion. Based on previous evidence, you believe the population proportion is approximately 20%, or 0.2. You would like to be 98% confident that your estimate is within 2.5% of the true population proportion. How large of a sample size is required? Well, let's first find the critical score associated with 98% confidence. So if we want to be 98% confident, that leaves us with 2% to be split among the two tails. In other words, there should be 1% or 0.01 to the right of my critical value. So looking this up on the table, and make sure you agree, the critical value with 1% to the right is 2.33. Now let's calculate the sample size. We found our critical value. What we need to do now is find p hat, q hat, and our margin of error. Well, p hat we decided was going to be 0.2 because based on previous evidence, we're expecting the population proportion to be 0.2. Q hat then would be 0.8 or 1 minus 0.2. My margin of error is going to be 2.5%, or in other words, 0.025. So plugging all this in, and be sure to square what needs to be squared, that is, square the critical value and square the margin of error. But I get that we should sample 1,389.8 people, which I'm going to round up to 1,390.